typing on the Terasic DE1 system on chip board by synthesize a constraint design of 32-bit up-down counter and observing the four most significant bits of the counter output to LEDs on the board. So open the Quartus Prime and create the new project, and next, and we're gonna choose where to put this design. So select this folder and put the name LEDs counter. Next, and we're gonna use this target device. Next, finish. So now we're gonna create a design file, and we're gonna choose VHDL file, and we already have the code for the project. And the so we're gonna just modify this line. So here should be 31-bit, and save it, and then we gonna compile it and check if everything's good. We're gonna pause the. So as we can see, the result of the compilation is good. And now we can see the resource utilization, how many lookup ALMs, logic module that this design utilize. And then we can do the timing analyzer. Sorry. And we can check the max frequency here. It's 409.67 megahertz. Next step is to create a test bench to check that this design is work as it should be. So from processing, start, test bench, and we can save it. Add the test bench file from here. We're gonna find it in simulation. Apply, okay, and we can set it as top level entity, and here we already have the test bench code, and then recompile. Yes. I'm gonna pause the video. So now we can do the simulation. So compile, go to choose the test bench, compile, down, and no error. And now we need to view the wave, and we need to select the signals we need to simulate. Clock, the counter, direction, and reset, drag and drop, and then simulate, and we can check here that this is the direction and this is the reset. We can just make it bigger here. This is the direction, and we can see when the direction signal is 1, the counters goes up, and when it's 0, it's gonna go down, and when the reset signal is 0, that's gonna reset the counters goes to 0, as we can see here, from 3 to 0. So the simulation looks good. So now we're gonna move to the next step. So in order to use this design to prototype the DE1 system on chip, we need to create a constraint file to declare the design constraint. So new Synopsys Design Constraint, and we have this. In my case, the only thing we're gonna declare is the primary clock for this design, and it should be match the clock signal we use in the on the top level input, and it's here clock, and they are match. And in this case, we are telling the Quartz and the Questa timing analyzer that the clock is the reference. This clock is the reference clock source for the top level design to do timing analyzer. So save it, and then recompile. So in order to observe the 4 most significant bits on the counter output to LEDs on the board, we need to do some change on the top level design code. So those change is like, we don't need all those bits to be like observed on the LEDs, because we're gonna use like 50 megahertz frequency on this design, and we cannot observe the lids when they are blinking in high frequency. So we're gonna use only the the 4 most significant bits. So we're gonna change this from 3 to 0, and here we're gonna change this from 31 down to 28. And then compile again. So the other constraint we have to do here is the pin assignment. So actually we're gonna connect those entity ports, clock, reset, direction, and the the counter output to the physical pins of the Cyclone V. So we're gonna go to the tool and choose, well, not sorry, it's in the assignment. Go to pin planner, and the way that we need to connect those pins is like as in this picture. So the clock should go to this pin, the count 3, count 2, and direction and reset. So input the okay, I'm gonna pause the programmer, and from hardware setup, choose DE1-SoC and auto detect, and use this device. Okay, so now we need to change the file. So go to the output file .sof file, and choose it and start. And it's 100% successful. That means good. So as we can see here, when we download the program on the device, so we have the 4 most significant bits, 1, 2, 3, 4 LED. So this is the direction switch, and this is the reset switch. So you can see here it goes up, and when we press the reset, it's gonna go to 0 and start counting from 0. One, 3, 4, And if we flip it to down direction, it's gonna go to down. 4, 3, 2, 1. Zero, and go back to all on, and again when pushing the reset it goes to